I'm Michele Grossi. I would like for sure to thank the organizer to giving me the possibility to share the CERN Quantum Technology Initiative. And so I prepare an outline of my talk that I hope that fit the subject of the conference. And I regret not having the possibility to be there, but I hope to give my talk the best also on the remote location. So the outline of my talk is divided in 4 parts. At the beginning, we give a general introduction about CERN, for those of you that are not on the subject, on the field. Then we will talk about the CERN Quantum Technology Initiative, and in particular, we will focus on quantum research domain, so the research areas that we defined to invest for our quantum technology initiative. And in the end, I want to give some overview about the intersection between classical and quantum computation and how we are using our HPC system together with quantum computer. So, brief introduction about CERN. Describing CERN in a few minutes, not easy, but essentially it's a place where people do research on fundamental research, let's say. And of course, it's an international organization located to Geneva, and it is composed by different member states, so more or less a lot of countries here in Europe, and also we have partners for outside Europe. A lot of people, we have around 3,000 staff members and more than 13 associates. So there are a lot of people working here on site, but also as an external collaboration. Of course, CERN is a place where people study different things. It's not easy to describe all of the topics of the research that is done here at CERN, but I wanted to put some notes in this funny blackboard. So essentially, we work on understanding fundamental theory of particle physics and nuclear physics. And we have some research about standard model, about beyond standard model. So we want to understand how the particle interacts, how they interact with the detector, and in particular, if there are some effect of beyond standard model description. And then we have, of course, other pillar, essentially quantum field theory, string theory. And an interesting topic that is also part of the research domain for quantum computation is lattice computing. So this is a very important topic also from the computational point of view. And not only nuclear physics, but also cosmos and astroparticle physics are part of the research environment here at CERN. But how we perform research, so that's the important point to better describe and introduce the role of computing in our environment. So essentially, we work with data, a lot of data. So some of the data are generated by simulation. So we use some Monte Carlo techniques. We are using some quantum machine learning techniques to generate the data. But we have also a lot of data that are coming from particle interacting directly in our experiment. So we have the data acquisition process, and this is given by the ability to reconstruct how the particle interact in our detector. So we have the track reconstruction process that is a very important step, not only for calculation, but also from theoretical point of view. And putting everything together, we are able to do a lot of data analysis. In particular, we want to compare our models, so simulated data, with the data that we got from the experiment, so that we can understand if the model we are using is the right model and so on. And this was the basic framework that we used for this discovery, the famous Higgs boson some years ago. So we have models and we have data. That's it. Talking about data, so here is a sketch of what is the Large Hadron Collider, this tunnel that is located 100 meters under the floor, under the ground, and in 4 main points in this ring, particles, in particular proton and antiprotons, interacts and generate a lot of particles that decays, and we can measure them with our detector, and then we can collect the data. But we collect a lot of data, so we have a complex process of triggering a lot of data. We have this rate of collision, which is 1 petabyte per second, which is a huge and tremendous amount. After some hardware level filtering, we need to split a lot of data to many points so that people can work and do some computation. And for this, we have the worldwide LHC computing grid. That is a complex grid located that is distributed around the world. And in Budapest, there is a big data center as well, when we split our original in different tier architecture. So that's a very important step for our computation. So Quantum Technology Initiative for CERN has been built during the last year, but in particular, we published it some weeks ago, and everything is online so that people can read. And of course, we got many feedback already and proposal to contribute to our technology initiative. Essentially, this Quantum Technology Initiative represents the quantum initiative for the CERN member states, in particular the CERN community, the worldwide LHC computing grid. So everyone that in some sense are collaborated with the current LHC scenario and experiment. So there are four main ingredients in this initiative. We have the scientific and technical development and capacity building. We have the role of co-development. So we want to develop together some software stack and some algorithm with other parties. There is the goal of community building. This is an important topic in particular for a new topic like quantum computing. And then we want to integrate with national and international initiatives and programs. And this is a complex scenario at the European level, but also at the worldwide level. So we have a lot of university and nations that are investing in this technology, not only academics, but also industry. So we want to work as a reference point and hub that is able to collect and integrate those kind of effort. Here in this slide, a short overview of what is going on in Europe, for example. You see that every country more or less has its own national initiative for quantum computing. For example, in Spain, the Quantum Association, we have the French Quantum Plan, we have the Dutch National Agenda on Quantum Technology. So that means that every country is at different level investing in this technology. So CERN, for its role in the high energy physics scenario, but also as an international organization in the middle of Europe, we want to work to attract and coordinate and integrate with some of these initiatives. It's important to have within this kind of initiative an advisory board. So this is a close relation with the CERN member state, of course, and this is an ongoing activity that is recognized, of course, as a fundamental key of success. So the integration of the member state. And apart from that, we have the establishment of this advisory board that is composed, of course, by qualified experts from all different member states that can encourage and support and guide, in some sense, some initiative within this framework. Now we have published this Quantum Technology Initiative, so you can also have a look at the members that are part of this advisory board. Not only academics, as I was saying, we have different research institutions that are actively collaborating with us, and also companies. So in this picture, you see a lot of logos that belongs to different organizations and companies. Some of them are more focused on software side, so they are developing software for quantum computing and integration with classical computing. But also we have companies that are working merely on the hardware side, and in a more complex scenario, we have companies that are working on both sides. So they are building hardware and also they are building software. So it's a very active environment with a lot of companies, from the biggest one to also small startups are emerging to contribute in this field. Last a very important news about CERN related to the interaction with companies is about the joining of CERN within the IBM Quantum Network. So it is a complex organization where a lot of industry and academics are collaborating to produce new research papers, so to advance the research in this field, but also to support the industrial use cases developing of quantum computing for their usage. So very recently, CERN signed this agreement, that is for the moment for 3 years, and so we are really actively looking for other partners that want to join our network. And now we can say that we are a quantum hub, so we can give access to IBM machine, and also we can provide support for any kind of research project. But what are these research projects? So what is the research? What are the research domains for this CERN Quantum Technology Initiative? So we can think about dividing, the whole research scenario in four main pillars. First one is the one when I work in is the computing and algorithm. So in this case, we are working on performance, simulation, reconstruction, and classification tasks using also quantum computing. So we are combining classical and quantum computation to create and explore new type of algorithm that can improve the performance of current state of the art. Second topic is, second pillar is the sensing. So the idea here is to create and develop new sensor, new detector that can exploit quantum computing and in particular quantum phenomena. So both for low energy and high energy scenario. This is a very interesting topic. The third one is about communication. And in particular, I will spend some words on this topic later on, but essentially we are working with the possibility to create a quantum a QKD infrastructure, and in particular looking for quantum internet implementation. So CERN has a special role in the internet scenario, of course, for the WWW invention. So we want to make other contribution also in the quantum scenario for internet. Last but not least, of course, theory. Theory is strictly related to quantum field theory, of course, and quantum computing can, in some sense, provide an advantage. So it's one of the origin, coming back to the original idea of Richard Feynman to build quantum computation, to exploit, of course, a different machine that can speak the same language as the quantum theory. So in this case, I want to mention lattice quantum chromodynamics as one of the main topics for our research area. So if we want to summarize some of the points that we are working on and the way we can define the strategy for the Quantum Technology Initiative, of course, we want to give access to quantum computing potential in high energy physics scenario, but not only. So that is to develop and optimize current algorithm and target them for realistic use cases. And they could be created looking for the NISQ era, so some algorithm that can run nowadays to the current hardware, but also in the ideal scenario. So a lot of companies are looking for fault-tolerant quantum computers, so we will have a logical qubit, and in that case, we want to have also algorithm. Of course, then we want to build expertise on the state of art for the software stack. So the combination of software plus hardware is one of the most important things to communicate with the quantum computer. So we are working on simulators, so in particular with GPU integration, and we are trying to understand how to create the software stack with different hardware, and in particular, agnostic with respect to the final device. Then we are working on optimization, of course, for classical computing resource, because we will see that a lot of the current algorithms are hybrid algorithms. That means that we work with quantum computer, but also with classical computer, and the classical part is very demanding in terms of computing resource. So it's important to create the right balance and organization. And for this reason, we want to set up a distributed quantum computing simulation platform. So at CERN, users are used to work with simulation. We have our platform, so we want to provide access to a complete platform that can include also quantum computing, not only from the real hardware point of view, but also for the simulation point of view, and we will see why simulation is important also for quantum computation. We are working, as I said, on some quantum machine learning algorithm. We are looking for variational approach. We want to understand the role of the noise, so the running on the real hardware on the result of our algorithm. And we have interest in quantum computation as an algorithm in general beyond quantum machine learning. So quantum machine learning is just one section of our goal. Now we want to have a more formal approach to the algorithm. So we don't want to take something that is already provided in the literature. We want to contribute actively to this field. And to do that, we have different collaborations so that we have the possibility to run our algorithm not only on the semiconductor platform like the IBM one, but we have the possibility to run on photonic platform, ion trap platform, and atom-based platform. So we have the possibility to explore the properties and the performance in different scenarios. Now, in the following, I want to show you some example to be more concrete about what we are doing in the algorithm section. So in particular, in this case, we are talking about quantum machine learning. Here is just an example of an implementation of a hybrid classical quantum generative adversarial network. So starting from a different paper that was written for a finance use case, we took this algorithm to load the probability distribution in quantum states, and we were able to reproduce one-dimensional and two-dimensional energy profile of a calorimeter image. So this was one of the first attempts in this field. So you see a sketch in the left bottom part of the slide. We have this configuration, which is a variation of circuit that essentially works in this way. So we have this quantum circuit, we execute it on the simulator on the real hardware. Then we have to update our parameters. So we move the information to the classical computation that with some optimization routine give us the new updated parameter, and then we close this iterative loop, which is very important in terms of communication between the quantum and the classical side. And with this, we got the possibility to reproduce real image that reconstruct the track of the particle within a calorimeter. So it was very, very interesting. Very similar to this, but with a completely different approach in terms of hardware and in terms, if you want, of quantum computing formalism. We are working on continuous variable because we can work on a photonic-based platform. So in this case, we move from the standard qubit semiconductor platform, so digital simulation, to a continuous simulation to perform a similar task. So here we created our hybrid model that was made with a tool called Strawberry's Field plus Pennylane and integrated with NumPy backend. So in this case, we have, again, a collaboration between the quantum side and the classical side, both from computation and both from real hardware point of view. So there are pros and cons about those two approaches. The last example I want to mention here about quantum machine learning implementation and the role, again, of computation is the quantum version of a very well-known classification algorithm like supervisor machine. In this case, we tried to somehow redo the task of classifying the Higgs boson events that we have here at CERN. And we used the quantum supervisor machine that was published a couple of years ago. And in this case, we were able to load our data, to encode our data in quantum circuit. We were able to train our quantum supervisor machine. And what we wanted to do is to compare the result that we know that we have from classical side. So usually we can use standard deep neural network to do this sort of classification with respect to our quantum supervisor machine. And in some sense, with a very few number of events with respect to the standard case of the deep neural network, we were able to have a comparable measurement and performance. So that's a very interesting result. And I mean, the AUC and the accuracy were comparable. So we are very confident that this model will give us a very good result in the future. Moving to the second pillar that I showed you before about our initiative, let's talk about Quantumacy. And Quantumacy is a project that is using the open source quantum key distribution protocol, and is basically a quantum-based privacy and self-determination service. So here we have some nodes at CERN where we can implement physically the quantum key distribution. And so we are trying to secure in a distributed way the analysis that we are performing at CERN. So we want to use quantum key distribution as a protocol to secure the distribution of the information for the data analysis. So that's very, very important. And we are using quantum homomorphic encryption, and we are working on using as auditing technique quantum blockchains. So that could be very interesting, not only for simple analysis or messaging that we can share between the nodes, but we can think about extending this protocol to a more complex scenario, not only for high energy physics analysis, but also, for example, in medical use case, where you have to analyze image and so on. So you have to use your model and you have to encrypt your data. Now I want to move to the last part of my talk, which is more related to the role of the computation and the interconnection between classical and quantum computing. Quantum and classical computer are complementary. So usually we say that quantum computer will not substitute our computer. We will still have conference on our current laptop. Something will not change, of course. Quantum computer born for specific task, and we have the proof now with a lot of literature that has been published that quantum computers are very good for some specific task. And the idea is that in general, as we are doing now, quantum computer will be used in actively collaboration with the classical computation, because standard classical computation are good to store, manage, and process huge quantity of data. And here on the left side, you see a picture from our data center here at CERN, Tier 0 data center. So classical computers are good for that. So storage and process huge quantity of data to extract insights and take business action. But some of the tasks that are done with classical computer can be done better on quantum computer. So maybe we have complex machine learning model to implement. We have some optimization problem. And then we have some of the most famous quantum algorithms, like the Shor's algorithm for the cryptography problem, and so on. So we know that there exists some specific topic, and so we need to construct this collaboration in the best way, in terms of efficiency and in terms of, for example, time delay between the communication of the two. So with quantum computer, we can explore a large set of possibilities. We can identify optimal answer, but of course, we cannot store information. So that's why we need this continuous iteration. The idea here at CERN is, as I said, is to create a quantum computing platform. And the idea is to create a unified quantum computing platform that is based on different open source tools like Docker, like Kubernetes, and so on. And in this case, we can give the possibility to the user to start from their problem as the same way they are doing now today, and implement our with our quantum computing platform. They can use different hardware, so we can use semiconductor qubit, we can use ion-based trap quantum computer, and different simulators. So you see in the right part of the slide the possibility to choose for the user a different platform, a different technology to run their computation. So it's a way of extending the ability of our user to perform computation and analysis. So I said that sometimes we need to use a simulation of quantum computing, and we need to simulate quantum computing because, of course, there are now not a fault-tolerant quantum computer. So now quantum computer can be simulated because the dimension allows us to do that. But this is a challenging, of course, and because we need to simulate quantum computer, we need huge classical computer with a lot of power in terms of computation. Why is a challenge for quantum programming? Because qubits are not analog. Quantum programs result in a probabilistic output, so we completely need to change our setup in the way we do the things. And of course, we can't read the entire exact state of a quantum program, so we need to understand what we are measuring. And of course, each device and each qubit has its own characteristic. So the problem is that at some point, the programmer should understand how the hardware is working. So since we want to work with different kind of hardware, different species of hardware, this is a very important task. And of course, there is no data input to a running quantum program. So the way we encode the data, it's another important task in our scenario. Sorry. Oh. Okay, sorry, I'm back. Okay. Let's see. It's like having a review of the talk I gave. So, okay, we are here. I don't know, sorry, I don't understand what's going on.
No, be.
Okay. I hope you can see my slide as well.
Yeah. It's perfect. Yeah.
So I want to talk about the simulation of quantum computer. Why I want to use simulator? Of course, we want to use simulator to prototype and understand quantum algorithm before running on the real device. Why is it we want to do that? Because run a real device can cost in terms of money, in terms of resources. So we want to understand the algorithm before investing on this. We want to simulate on large quantum system, and in general, this is an exponentially hard computational task for a classical computer in terms of memory requirement. So the simulation of quantum computer is important, but at the same time is exponentially hard, and it's doubling the memory requirements for every qubit we add. And this is in fact one of the motivation, of course, for building a quantum computer. Now, for the time being, it's generally cheaper and easier to run an experiment, at least a small scale one, on a simulator. And this is a very important task. So it's not something that seems to be less important, because the moment where we found ourselves is the way we can benchmark what we are doing on quantum computer with classical computation. Because very soon we will reach the limit where we cannot simulate anymore any sort of quantum computing, because when we exceed a certain number of qubits, we should rely on what we have done before. So that's a very important thing. And then with simulation, we can also understand the property of the noise of the device, and we can do a sort of simulation about what are the elements that affect the performance of the hardware itself. Okay, so as a summary, we can say that simulating on a quantum computer is something that we can do, and we can understand more or less this looking at the plot here on the right side of the slides. And we can say that we are getting to the point where experiments are being run which are difficult to simulate classically. So it's very, we can say that we are at a turning point when we can test our small-scale quantum algorithm, and then we are ready to run them on the real hardware. And when we will exceed a certain number of circuits, here I put an example of a complex scenario, we should rely on what we have done before. So that's a very important thing. And in the plot here on the right, so there are two directions where you can understand the way you can simulate. You can simulate state vector and density matrix of your quantum circuit, and this can be done for low level of entanglement. So that's why it's very complicated to simulate a quantum computer on a real, to simulate a quantum computer with the classical computation. BACUS project is one of the last project I want to mention in this call. So it was started by one of our summer students this year. It's a way to automate the way we benchmark the use of the hardware and the use of simulator. So it's a preliminary platform that we use to provide all of our users to have a unique platform to test their usage of quantum computation, both in terms of simulation and both in terms of assessing the performance of the real hardware. So in this case, you will see different installation and different implementation of our simulator using CPU and using in particular GPU. A lot of the software stack that are available today are somehow optimized to be used with GPU. So that's an important thing. A few things I want to mention before the closure. The idea of this quantum technology initiative is to build a quantum infrastructure. As I said, CERN started the web, so there is some expertise here, and this is part of the DNA of CERN. And the idea is that, again, in collaboration with the EU and other international network deployment, we want to integrate quantum computing in the current computing architecture. So we want to create a sort of quantum infrastructure, and there are already different proposals in this sense, so that quantum computer can be one of the elements of a general infrastructure for quantum computing. Let me close with this last slide. So we cannot build all of this platform and all of this knowledge in terms of algorithm and scientific publication without a proper education program. This is a very important topic for us, and I can see from different talk that is an important task also for many other research institutions and industry as well. So for this reason, we are working on a specific education program for quantum computing activity. And for that, we organize several lectures and seminars with field experts, of course. We organize several training courses. We got colloquial and specialist seminars. And what we will do in the near future is to organize the hackathon. Hackathon are the best moment where people and students can meet and create and improve the technology, creating new algorithm and maybe new architecture framework for this usage. And one of the examples that we have with this kind of initiative is the summer student program. This is where, for example, the project BACUS was born. With that, I'd like to thank you all for the attention. I apologize for the last few minutes in this strange format, but I got this problem. So thank you so much.
Thank you very much, Michele. We really appreciate. This is a real. So just a few remarks that I missed Hungary from the map you showed in the very beginning, that we also had this CERN QTI Hungarian quantum technology for a long time ago. I think it was somehow not added to the at just a certain point, which is just ended. It's very funny in this in a few months before. And we started a new quantum technology initiative also in Hungary in a slightly different way. And actually our institute is, and then the GPU laboratory, which is not only GPU, of course, but we are on the way to connect hardware-wise to the quantum simulation, quantum computer simulations. And this is why we had previous speaker, Oscar Menser, also because we bought one of his latest machine in order to do bosonic sampling. And we will have some talk, and the previous talk, and then one of the forthcoming talk will be also about this thing. So I think we would like to put a more stronger emphasis on the map of this technology initiative from Hungary as well.
Sure, I will update the slides and we'll communicate this internally. And of course, I hope we will collaborate soon. So
yeah, me too. So I'm very happy to see you also here. So further questions from the audience, either from outside or online. Simbi wanted to say something.
Yes, I thanks a lot. Maybe I show myself. Hi. So I wanted to ask you about your initiative concerning these quantum simulators. So those that you mentioned were like about qubit based, although you mentioned some results about continuous variables. Is CERN interested in building up something concerning continuous variable, so photonic quantum computer simulators, or you are mostly concerned with qubit-based architecture?
No, I would say that we are open to both scenarios because, I mean, it's not so clear what will be the real and the most prominent quantum computer technology in the future. So we know what the industry are doing today. So we know superconducting qubits, so we know atoms are coming up in the field. And so we need to understand where to position our simulator, because in the end, the idea is, as I was explained, is to use simulator to simulate what you can do with the real hardware. So it's important to have the possibility to simulate all different technologies. So I'm pretty sure we will invest also in this field. And in the work I was presenting, it was done with strawberries and penny laying. This is a simulation of continuous variables. So that's it. Yeah.
Yes. So I have another related question. So you put a lot of emphasis that CERN in these when building these simulators is using also GPUs, which is of course very pertinent in a GPU days to mention this. Have you thought about using FPGA? I mean, in this, as Gergely mentioned, we have this Quantum National Laboratory now in Hungary, and for example, within the context of this, we are building these type of simulators, mostly continuous variable. And Peter, the previous talks, actually, he showed this FPGA approach, which is based on Oscar's setup. Are you also going towards using FPGAs instead of GPUs, or in conjunction with, perhaps, even?
I would say that, of course, there is, I mean, regarding FPGA, there is a lot of people with high skill here at CERN that are working on that for different topics, you know, for trigger and so on in some experiment. And we will use all of the knowledge that we have at our hands to implement the simulator. So FPGA is, of course, one element that could be evaluated. And there is no, it is my understanding, there is no currently an active program on that. But of course, we are still discussing. I mean, we just published the roadmap. We are collecting the feedback. One of these could be one of the feedback. And so I would say that this is worth investing also in the idea of using FPGA as a simulator. What I saw in the literature and some initiative by some companies is that since you want to accelerate the interconnection between quantum computer and classical computer, there are some usage of FPGA on the real part of the quantum hardware. So in the way you compile the circuit, which is an NP problem, so you need a lot of computation. So they are trying to think about putting FPGA in a classical computer, but near the quantum computer, because you need low latency to do this kind of calculation. So it should be understand why and where to put this FPGA, but of course it's a useful resources to implement. Yeah.
Okay, thanks a lot. Yes.
I can see a raised hand by Attila. Attila, are you here?
Yeah, I was considering saying something for a moment, but yeah, I'll say some more things about FPGAs tomorrow. Not a whole lot more, but at least a little bit more on their experiments try to use FPGAs.
Okay, thank you. Michele, just to inform you that we will have a separate event following GPU Day in the afternoon. This is IME Academy Industry Matching event. If you are interested in that one, we can also send you a link. Yeah, I think you are not registered for that. You are muted now.
Okay. Yes, I was muted. Yeah. If you can send me, I will try my best to join. Yeah.
There is one question from the audience. Speak up, please. Speak up. The question is whether this technology can be applied to speed up the chemical analysis and chemical methods also. I think yes, if you can find a way to, but maybe Michele, you can also.
So regarding chemical simulation, I would say that this was one of the first topic that was initiated by the research community for building quantum computing. And there are a lot of paper on that. And I would say that they are using principle some variational method where they can do some statical analysis. So you can calculate the ground state of your molecule, you can calculate the electronic configuration, but also there are many different methods to do some real-time dynamics. So you can essentially evolve the system and solve the Schrödinger equation. And very recently, there are some proposals to improve the method that are currently used, which is the ab initio method to study those kind of materials. So quantum computer, I would say that we touch maybe the quantum advantage for, in particular in this field, because it's quite easy to understand where we need to improve and where is the algorithm that